In today's lesson, we're going to be talking about the inverse of a function. So first thing we want to look at is how do you find the inverse? Well, visually what the inverse is the inverse is a reflection in the line y equals x. So for a given function f, the inverse of that function is created by reflecting the function in the line y equals x. Let's take a look at an example of how that would look. So I have a graph here. This is the graph of y equals 2 to the x, let's say. And so exponential growth function. And what we want to do is to create the inverse of this function. What we do is we reflect this function in the line y equals x. Therefore, for a fixed point, let's say a, f at a, we are then going to reflect that in the line y equals x. So what that does is it creates a mirror image about the line y equals x of that point. So essentially what happens is it results in just interchanging your x and y values. Let's do that for a bunch of these points. So again, I've chosen a bunch of points on our line here, and we're going to go ahead and reflect these in the line y equals x. By the way, this intersects at a 90-degree angle, and by doing so, what we've done is we've now created the inverse of y equals 2 to the power of x. And this is illustrated by the reflection in the line y equals x. Now what that results in algebraically is just interchanging your x and y values. So for x and y, we just simply interchange the x and y values, and now you've had your reflected function. Let's take a look at some examples of doing this algebraically. So for our first example here, we want to find the inverse of y equals x minus 3. So first, let's change the f at x to a y. Now again, as we saw in the visual demonstration, it amounts to just interchanging your x and y values. Therefore, we interchange our x and y values, and we solve for y. Solving for y, I get y equals x plus 3. So therefore, f inverse of x is equal to x plus 3. Let's try it for the next one here. So same idea here. We'll change that f of x to a y. Now we interchange our x and y values. So everywhere you see an x, you change it to a y. Everywhere you see a y, you change that to an x. So it turns out we got to change it twice on the right-hand side. So now you see here, I want to be able to solve for y, but I have two y values here. So what I'm going to end up doing here is I'm going to complete the square on this to get this in terms of one y value. So let's go ahead and do that. And as you can see here, I started the process of completing the square, right? You find your b value, divide it by 2 and square it, you add and subtract them, and then you force a perfect square here as we did. And now again, if you've forgotten the process of completing the square, I'll link that in the top right hand corner. But now I've got y sort of compacted, and I can kind of isolate for y now. So I'm going to go ahead and subtract 3/4. Then I'll go ahead and take the square root. And you notice you have your plus or minus when you take your square root, and there's my final answer here. Now, this is the inverse of our function. However, we'll talk later about if there's some conditions, like is this actually a function when you take your inverse? Is it not a function when you take your inverse? And that's something that we're going to want to explore a little bit later on in this lesson. But for now, this is your f inverse of f, but possibly some conditions have to be put on the domain to make this a function. All right, let's take a look at some more examples. So for the next example here, again, you're going to want to go ahead and interchange your x and y values, and then take your cube root. Taking my cube root here, I get the cube root of x minus 2. So now I have here that f inverse of x is the cube root of x minus 2. And just as a quick illustration here, what we have on the right-hand side is we have the green line represents your y equals x line. Below that is our y equals x plus 3 example we were looking at. And then in purple, we have our y equals x minus 3 inverse that we had found. So you can see here with this example, you have your reflection in the green line, the line y equals x. This becomes your function in black was our f at x, x plus 3. And the function in purple was the function f at x equals x minus 3 that we had discovered. Let's take a look at the cube root example as well. So with the cube root example here, what we have in red was our original function, that's y equals x cubed plus 2. And then in blue here, you have your inverse function, x minus 2 to the power of a third, the cube root of that. So you can see here, y equals x is the line that it's reflected in, and you can see, again, anything that falls on the line y equals x, like for instance here, we have a point on the line y equals x. When you reflect that point, it's going to be still on the line y equals x, and you can see that illustrated in that intersection. But again, here we have our function and its inverse. So you can see they are mirror images of one another in that line y equals x. So continuing on here, this is your definition of an inverse. If a function is, when you find these inverses here, if a function is invertible as we see here, when you apply the function f inverse to the original function f on the left or on the right-hand side, you always get your x value back out. They would say that f inverse composite f or f composite f inverse acts like the identity function. And again, the reason they call it the identity function is when f composite f inverse or f inverse composite f acts on any input, it just gives you that input right back out. So they call that the identity function. This is a common property of all invertible functions. So anytime you calculate your inverse and that inverse is defined on that domain, it has this property right here. Let's take a look at applying this property to an example. So for the following example here, they give us the function, just a linear equation, 2x minus 3. Let's go ahead and find the inverse first. So to find our inverse, we're going to go ahead and interchange our x and y values. Then I'm going to solve for y. So solving for y here, I get f inverse of x is 1/2 x plus 3. So I've calculated my inverse here. I want to show that f inverse acting on f or f acting on f inverse will both yield the identity function. So take a look here. I first am going to calculate f inverse composite f. Doing so here, you have first f at x acts on the function, so f at x is 2x minus 3. Now everywhere that I see an x in my inverted function, I'm going to put in a 2x minus 3, so this will be 1/2. And then in place of that x value, you can see I substitute that with a 2x minus 3. And right away, you're already seeing this, the 3's will cancel, and the 2's will cancel, and our output is left with an x. Let's try the other way. And again, working with this function here, now f inverse acts first, in which case f inverse is 1/2 times x plus 3. Now everywhere I see an x in my original function, I'm going to change that to a 1/2 x plus 3. So that's our original function right here, and you can see I did that right below here. And now you'll see we have cancellation. The 2's will cancel, and then when you distribute this, the 3's will cancel. And once again, we're left with an output of x. So therefore, that verifies the property, at least in this example, that when f inverse acts on the right or the left, you just output your input right back out. So it just becomes the identity function. Let's take a look at some observations. So one observation, as we were kind of hinting at before, is that reflecting some functions in the line y equals x don't always create a function right back. For instance, here, what I've done here is I've got your function y equals x squared. You'll notice if I reflect the line y equals x squared into our y equals x line to create your inverse, our inverse would actually look something like this. But notice right away, looking at this function here, you can't really label this as a proper invertible function because this fails the vertical line test, right? For a given x, we have two different outputs, and therefore this is not a function in its current domain. So some functions, when you go ahead and actually calculate the inverse, it creates a relation that is not a function. So in this case here, by restricting the domain, we can then create a function with the inverse. So that's what we want to look at here. In general, and this is an important observation, if you have a function that fails the horizontal line test, then its inverse will not be a function unless we restrict the domain. And that example is illustrated here. We have the line y equals x squared. You can see this would fail the horizontal line test, i.e. for a given horizontal line, the function intersects twice. And therefore, when you calculate your inverse, it's going to therefore fail in the x-axis, creating not a function. So we're going to go ahead and restrict our domain and look at some examples of that. So in our first example here, we're going to go back to the line y equals x squared, but we're going to restrict the domain of that to go from 0 to infinity. And you'll notice that's illustrating the graph here, right? We've got our y equals x squared graph, but I kind of started it at 0 and then going off to infinity. So we're ignoring the negative. By doing so, when we calculate our inverse, we get the following. You can see here now that calculating f inverse, we do not fail the vertical line test. You're not going to have a situation where for a given x, there's two different outputs. And that came about because we restrict the domain from 0 to infinity. By doing so, we ignored having the left-hand side of this quadratic, which would have ended up coming down here, and then we would have had issues regarding the inverse being a function. So by restricting the domain of your original input, your original function, you then can create an invertible function. Let's take a look at some other options that we could have done to create a function. There was nothing really unique about what I did. I restrict the domain on the left-hand side. What I can do now is only consider domain of your function f at x that comes from the negative side. So we can restrict our domain to be from negative infinity up until 0. By doing so, a reflected function would look like. And you can see here again, restricting this domain, we still have an invertible function. It does not fail the vertical line test, so we're okay with this restriction. And this would be another option. So there wasn't really anything unique about what I had done above. You can also restrict the domain from negative infinity to 0. Let's take a look at another example. So for the following example here, they give us another quadratic. I notice this one is not centered on the origin, but same idea, we can go ahead and calculate the inverse of the following function. But again, notice that this function fails the horizontal line test. So right away we know that we're going to have to restrict the domain. So let's take a look at some other examples. Some options for restricting the domain are you could restrict the domain from 2 to infinity, right? And again, remember our original function looks something like this. So by restricting the domain, now we're just considering this part of the function, in which case its inverse would be a function and would look something along these lines. Likewise, you can restrict the domain from negative infinity to 2. Again, you're using that vertex as the breaking point in your quadratic where you want to go ahead and do that. So I can go from negative infinity to 2, and then the reflected function, the inverse, would exist on this domain. Another option, again, you don't have to restrict the domain right at the vertex. We could have restricted the domain from 4 to infinity, right? So your function actually goes along these lines here, and you say, okay, I'm going to restrict the domain, start at 4, which is right about here, let's say, and go to infinity. Then again, your reflected point would be right somewhere along this line, and would look something like that. Still a function by restricting the domain from 4 to infinity. One thing worth noting is if you did restrict the domain from 0 to infinity in our example, then the inverse would not exist. Let's take a look at why. So again, had we restricted the function from 0 to 3, our inverse would not be a function. We can see this already because our current function under this restricted domain fails the horizontal line test, and therefore its inverse, f inverse, would not exist. So again, you still have to choose your restriction properly so that your restricted original function does not fail the horizontal line test. You'll notice above, if we go back to our previous examples, all of our restricted domains here all passed the horizontal line test, as did this one. So then when we go ahead and calculate our inverted function, it passes the vertical line test. All right, let's take a look at some more examples. So for the following example here, they give us a function 1 over x plus 1, and they want us to go ahead and find the inverse, composition of functions, solve some equations here where f equals f inverse, and then f equals f composite f. So let's go ahead and take a look at these examples. So for the first example here, we want to find f inverse. So same process. We're going to let y equal 1 over x plus 1. So to calculate your inverse, you're going to interchange your x and y values. And again, I want to be able to get at this y value, so I'm going to multiply across by y plus 1. And then I'm going to divide by x. And finally, I'm going to subtract 1. So therefore, our inverted function, f inverse of x, is 1 over x minus 1. Let's take a look at part B. In part B, they want us to find f composite f at x. Well, by definition, that's going to be f acting on f at x, which is going to be f acting on 1 over x plus 1, which is going to be everywhere I see an x, I'm going to change that to a 1 over x plus 1. So I'm going to clean this up a bit here. Let's go ahead and get a common denominator in the bottom. And we'll multiply by the flip here and simplify where we can. And I end up getting x plus 1 over x plus 2. Okay, so we've got our f inverse calculated, and we have f composite f calculated. Let's take a look at part C. For part C, they want to know where is our original function equal to its inverse. Well, my original function was 1 over x plus 1, and my inverted function was 1 over x minus 1. So let's go ahead and get a common denominator on the right-hand side. Doing so, we get 1 minus x over x. So again, I want to solve for x here. I'm going to go ahead and multiply across by x times x plus 1, giving us. I'm going to distribute the right-hand side, in which case we get x minus x squared plus 1 minus x. Simplifying, we see the x's on the right-hand side will cancel, leaving us with x equals negative x squared plus 1. Bringing everything to one side, we get negative x squared minus x plus 1. Again, it's always a good idea to get rid of negative leading coefficients when you're factoring. I'm going to go ahead and use the quadratic equation here. This gives us negative 1 plus or minus. The discriminant here is going to be b squared minus 4ac over 2 times a. So I'm getting my x value here is negative 1 plus or minus the root of 5 over 2. So therefore, the function and its inverse should be intersecting at negative 1 plus root 5 over 2 and negative 1 minus root 5 over 2. Let's take a look at part D. For part D, they want to know where does your original function equal the f composite f function. Well, my original function we found to be 1 over x plus 1, and f composite f we found to be equal to x plus 2 over x plus 3. Again, to solve this here, we're going to have to get everything up in the numerator, so multiplying across by x plus 1 times x plus 3 we get. Again, the goal is to solve for x, so I'm going to expand the right-hand side and simplify, giving us. And again, I want to solve for x, so I'm going to bring everything to one side and simplify. Going to solve for x here, if I go ahead and calculate my discriminant is going to be b squared minus 4ac C, in which case I end up getting 8 as my discriminant. So this has roots, they're just irrational. Let's go ahead and use the quadratic equation to find where these intersect. Using the quadratic equation, we get x equals -2 plus or minus square root of 8 over 2. And that'll simplify to become -2 plus or minus 2 root 2 over 2. So you actually get two values where f equals f composite f, and that's at -1 plus or minus root 2. So here's another example here, kind of looking at this function here. And you'll see here that, like we were talking about here, the function equals f composite f at these values. So taking a look at a quick diagram here, function in red is f inverse, and the function in blue is our original function f. I just want to show you guys, this is where it intersects here. So this is where the function f and f inverse meet. We're getting here at 0.618, and -1.618, and -1.618. So these two values here would represent our two answers that we had found in that question. This is just decimal place equivalence, but I think we had it expressed with radicals. But these are where the two function and its inverse intersect. So that concludes our lesson today on calculating the inverse of a function.